All right, so let's take a look at rotational kinematics and dynamics. And this is really mirroring Unit 1 and Unit 2, kinematics and dynamics. We always got to remember same kinematic equations, right? We just have angular displacement, angular velocity, time, angular acceleration, and these are what connects the tangential. These are the tangential accelerations, velocities, and distance traveled compared to the rotational motion to the linear motion. So they're identical. The only direction vectors, we don't have 2D rotational kinematics, thankfully, but so it's just like 1D kinematics. There's clockwise and counterclockwise in terms of the direction for the vectors, so you got to assign one of those to be the positive directions. But otherwise, it's identical to what we do in Unit 1 kinematics problem solving process. The graphs of motion are identical too, so the same thing about the angular velocity, the graph of angular velocity, the slope's going to give you the acceleration, the area is going to give you the angular displacement, just sort of angular versions of those things. Okay, in terms of torque, the dynamics portion is probably the most complex part of this to make sure you really get a handle on. First of all, we have the equivalent of F net equals ma, right? Unit 2 is dominated by doing F net equals ma. That means drawing a free body diagram and summing up the forces and setting equal to ma and the x and y direction. Net torque, again, only one dimension, so you don't have to decompose anything. However, you do have to know how to calculate torque. So we have to do the free body diagrams. Now, torque, remember, requires you to multiply R times an F. However, you need to be very careful. When you're doing rotational motion, there's always an axis of rotation, right? Something that you're rotating around or moving around. And then we always have to think about the force vector. Okay, so let's say I have a force vector like this, and we have an R vector from the axis of rotation to where the force is applied. And because the way they get multiplied is the R, there must be a component of the R vector perpendicular to the force or a component of the force perpendicular to the R. That's what you want to multiply. Basically, when something is rotating around, it's got to be perpendicular to that R vector. So when I'm pushing up, it's causing that rotation there, causing that angular acceleration. So it does require you to identify its axis of rotation. You have clockwise and counterclockwise direction. Torque causes angular acceleration. When the angular acceleration is zero, we call that a rotational statics or static equilibrium. So we have some equations where we balance the torques when this part is zero. Okay, but if we're doing dynamics, we have to know something about the rotational inertia. Rotational inertia for a point mass is I equals mr squared. That's the mass. It's a scalar quantity. It's analogous to mass in linear motion, but a couple of things. One, it's based on the mass, and the r squared, r being the distance from the axis of rotation to where the mass is located. The whole idea, intuitive reasoning of rotational inertia is the harder it is to rotate, the more rotational inertia it is. So if you look at your net torque equals I alpha equation, basically, if something has a larger I, then for the same torque, you're going to have a smaller angular acceleration. That's one way to look at it. Or it requires a larger torque also to give you the same angular acceleration. Again, more difficult to rotate. And so that's why it's based on the mass and based on the distance. Because the further away something is, the harder it is to cause an angular acceleration. The more torque it's going to require. The more rotational inertia it has, because it's harder to rotate something that's far away from the axis versus something that's very close. Rotational inertia depends on the mass and how the mass is distributed. When you're talking about systems, the total rotational inertia is you add up the rotational inertia of every object in the system. Okay. And something that's new that you need to know this year for the 2025 and going forward for AP Physics 1 is you need to know what we call the parallel axis theorem. Parallel axis theorem says if you're rotating around an axis that's not the center of mass, then you can calculate the rotational inertia. That means it's always easiest to rotate an object around the center of mass, and if you try to rotate off the center of mass, it's going to be more complicated. The way you do that is you take the rotational inertia through the center of the mass, you add md squared. D is how far you shifted the axes from the center of mass. So this is the distance from the center of mass to the new axis. So when I rotate things around other locations other than the center of mass, we have to use the parallel axis theorem in order to calculate the new rotational inertia. Okay, so overall for rotational dynamics, the problem solving steps look like this. Very similar to the Unit 2 problem solving steps, but let's just highlight a couple of things. One, you're going to draw the free body diagram, but you're going to place the forces where they are acting. We need a positional free body diagram in order to calculate the torques properly, because you need to know that R component perpendicular to that force to see if it exerts a torque. Gravity acts at the center of mass of an object. All other forces act where it makes physical contact with the object. So ropes where they touch. So the rules for the free body diagrams are identical. It's just now you have to place the forces where they're acting. The force from one special note is the force from a pivot or axle or hinge where it's rotating around is still a normal force, but because it's circular, because it's kind of round, the normal force can kind of point in any direction. Again, it is a reactive force like any other normal force, but you don't necessarily know what direction it is. It will respond to the other forces, maybe to keep it from moving, so the linear acceleration is 0, or things like that. The next step is you must identify the axis of rotation. This is sometimes a step that some people kind of don't understand or skip over very easily, but make sure you identify the axis of rotation. When the angular acceleration is 0, you actually can pick anywhere to be the axis of rotation because the angular acceleration is 0, so it doesn't really matter where you put the axis of rotation. However, if it is non-zero, you need to pick the point or the axes at which it's rotating around. Okay, and for rolling objects, you pick the center of mass of the object. So that's kind of some basic rules on where the axis of rotation should be. You need to assign positive and negative directions. This has got to be to the clockwise and counterclockwise as opposed to like left, right, or up or down. And for each force, we compute the torque, and then we add them all up. Net torque equals I alpha. If the angular acceleration is non-zero, you may need to calculate the rotational inertia, or it may be given to you. And if necessary, you might still apply F net equals ma. You still have a free body diagram. You might still use F net equals ma from Unit 2. Okay, so that's kind of the overall process. Let's take a look at a few questions here. So we have a uniform rod of mass m0 and length L is free to rotate about the pivot. On its left end is released from rest when the rod is 30 degrees below the horizontal. With respect to the pivot, the rod has a rotational inertia 1/3 m0 L squared, which the following expressions correctly represent the magnitude of the net torque on the rod about the pivot the moment the rod is released. Okay, so we draw a free body diagram. We're going to have gravity, right? Gravity acts at the center of mass because it is uniform rod. Center of mass is right here. Okay, what is touching it? Only the pivot. So the pivot probably exerts some kind of normal force upwards, probably not to the right, because if it was to the right, then that means the beam would have to accelerate to the right because there's no other forces. Okay, so we got to next identify the axis of rotation. Axis of rotation is right at the pivot. That's the natural point it's rotating around. And it's also the rotational inertia we know. So the normal force doesn't exert any torque because the R is 0. It's acting at the axis of rotation. Let's say clockwise direction is the positive direction here. So then mg is gonna be the only torque. We gotta draw our R vector from here to here, and that is L over 2, right? Because that's the length, and this is L over 2. Now, notice that the force and that R vector are not perpendicular, so we have to decompose it. You either decompose the force or you decompose the R vector. In this case, it's easier to decompose the R vector, and you want to take the component perpendicular. So gravity's pointing down, we want the component to the right, and that would be L over 2 cosine 30 degrees, because you have the angle here is 30 degrees, so that decomposition. So then the net torque is going to be L over 2 cosine 30 degrees times m0g times the force, and that equals I alpha. Well, the I alpha 1/3 m0 L squared times alpha. Now, they don't ask us to find that. They just ask for the net torque. Cosine of 30 degrees is root 3 over 2. Well, actually, they just have it here. So now notice they don't have any cosine here. So we got to, sometimes you need to be careful with the rule. You should know that cosine of 30 degrees is the same as sine of 90 minus 30 degrees. That is one of those properties of right triangles, so that's sine of 60 degrees. So all they did here was replace it with sine of 60 degrees. And so we need m0g L over 2 sine of 60 degrees. So that's going to be B there. Okay? So let's take a look at this FRQ here. So we have this solid disk of radius r, mass m, is mounted on a frictionless horizontal axle. The rotational inertia of the disk is given by 1/2 mr squared. A light inextensible string passes over the pulley with one end attached to a hanging block of mass m1 and the other end attached to a block of mass m2 on a frictionless horizontal surface. The system is released from rest, causing the pulley to rotate as the blocks move. Suppose the mass of the pulley M is increased, right? So as a mass M is increased while keeping the radius M1 and M2 the same. Will the linear acceleration of the blocks increase, decrease, or stay the same? So this question is really asking what's going to happen. So how is this affecting it? Well, when we did unit 2 and we had a rope that kind of went around here, we assumed that the tension was uniform. However, if you look at what's going to happen, if you draw a free body diagram of here and here, there's only two forces that exert a torque. The ropes exert a torque. Now, because we can't ignore the fact that there's some mass, there's some effort, right? Some net torque necessary to cause it an angular acceleration, these two tensions cannot be the same. Because if they were the same, there would be no net torque. They would have the same, because they're both going to exert the same torque around the center of mass here. So this torque has to be different. This tension has to be different than this one in order for there to be a net clockwise torque to cause it to spin clockwise. All right. So the end result is that you're going to have this net torque on it. Now, what is the impact of increasing M? Increasing M is going to make the rotational inertia greater. And with greater rotational inertia, it's going to be harder to rotate. If it's harder to rotate, it's not going to rotate as fast, right? For the same kind of masses there. So it's going to decrease. That's the reasoning, because increasing the mass will increase the rotational inertia. And what is rotational inertia? But nothing more than telling me how difficult it is to rotate. So the pulley will be more difficult to rotate. And have a smaller angular acceleration for the same torque. Okay, cool. Now we want to derive a linear acceleration of the blocks. Now, pulley systems, we're going to start with the free body diagram, right? So M1 has M1G going down, and it's being pulled up by the rope T1. Nothing else is touching it, so we're done. M2 has gravity M2G. It's got gravity. It's got a normal force from the surface. There's no friction here. And then there's a T2 pulling it to the right. That's all it's touching it, so we're done with those free body diagrams. This guy has T1 and T2. He's also going to have gravity, and there's probably something that's going to hold it in place. Some axial force. And it's got to be up to the right, because the pulley isn't like falling or going right or left. The center of mass is just staying there. So the net force has to be 0, but the net torque is decidedly non-zero. That's the distinction. So after that, we're going to do our F net equals ma for the blocks, and net torque equals I alpha. Or actually, we don't identify the acceleration. So this thing's going to accelerate right. This is going to accelerate down. And this is going to have a clockwise angular acceleration. So we'll make those the positive directions for the purposes of our F net equals ma and net torque equals I alpha. So for block M2, we only have one force to the right, and that's T2, and that equals M2 times the acceleration. For block M1, we make down positive, so the net force is M1G minus T1 is equal to M1 times A, because we made down positive, so this is a positive, this is negative. And then for the pulley, we're going to do net torque equals I alpha. Now, we're going to make clockwise the positive direction. We have to identify the axis of rotation, which is right there. And so that means the axle and gravity are not going to exert any torques. But T1, because the R is 0, but these are going to exert torques. T1 is going to do a positive torque, and it's already perpendicular to the R vector, so we just multiply it by R. T2 is going to have a negative torque, because pulling left would cause this thing to rotate counterclockwise, so that's a negative torque. Right? And that equals I times alpha, which is 1/2 mr squared times alpha. Now, the one thing that's going to connect them, you got to keep in mind, is as long as we're not slipping on this thing here, we assume with a pulley, is that the linear acceleration at the edge here is going to match this linear acceleration, and it's equal to alpha times r. So we're going to keep that in mind here. So first we can divide out an r on both sides. So cancel that and factor it out. So we have T1 minus T2 is 1/2 m, and then the r alpha we replace with a, this guy right here, because alpha times r is a. So then we have T2 is equal to m2a. Sorry, this is lowercase m2, m2a. and then m1g minus t1 equals m1a. And if you do a good job with the sign conventions, you just add these three up, because you have a plus t1 minus t1, that will cancel. You have a minus t2 plus t2, so the left side, when you sum it all up, just becomes m1g. And then the right side is going to become, you add all these a's, just factor out the a and add them up. It's going to be 1/2 capital M plus m2 plus m1. And so the acceleration is going to be m1g divided by this 1/2 m plus m2 plus, okay. Does your equation from part A agree with your reasoning? Equation for A from part B agree with your reasoning from part A. So we said increasing m will decrease the linear acceleration, and we see the big M, sorry, this is m1 here. This big M is only on the denominator. Yes. Increasing m increases the denominator. So A decreases, which is what we said. Okay. Let's look at another one. So a disk of rotational inertia I0, mass m, and radius r is spinning with an initial angular speed omega naught about a fixed horizontal axle. A constant frictional torque acts on the axle opposing the rotation. The disk eventually comes to a stop after making a certain number of revolutions. Suppose a block of mass m attached to the edge of the disk, and the disk is spun again with the same omega naught and the same frictional torque. Will the number of revolutions the disk makes before coming to rest increase, decrease, or stay the same? So we're talking about the number of revolutions. That is to say, like, how many times it goes around. That's like an angular displacement. Another way to think about that. And we want to think about how that's it. Now, what's the difference by adding in a piece of mass here? By adding in a piece of mass increases the rotational inertia of the system. Okay? And what that's going to do is, even though you have a frictional torque, it's going to be harder to slow down. Right? Because now you've added mass, you've made it harder to spin. It's also going to make it harder to slow down from that same torque. So if you apply the same torque, it's going to take longer to slow it down. And so it will increase. And then this reasoning is going to be the added mass increases the rotational inertia. Increases the rotational inertia, which makes it harder to slow down. So it will spin more. Spin more times around. Okay, so if we want to derive an equation for the number of revolutions the disk makes before coming to rest. Now that is an angular displacement, so we need to think about kinematics here. Okay, so the angular displacement, we'll say it's spinning clockwise at omega naught, and we'll make that the positive direction. So we would like to know the angular displacement. The initial angular velocity is omega naught. The final, it comes to a rest. And we don't know the angular acceleration or the tension, but we do know the torque. So we can use the torque to do the angular acceleration. So that's what we're going to do, is the net torque equals I alpha. And so then the net torque would then be this torque that they're giving us. Now it's gonna cause a negative acceleration because the torque is gonna slow it down. So that means the angular acceleration has to be this way, which means it needs to be negative, because we said the initial angular velocity, the way it's spinning, is the positive direction. So that will be a negative. So we'll make that a negative torque, and that's going to equal I0 times the angular acceleration. So the angular acceleration is negative that torque over I0. Like that. So now we know three quantities here, and we have a fourth quantity. So we're going to use what kinematic equation relates those four variables is going to be this kinematic equation. So that's going to be 0 is equal to omega naught squared plus 2 times negative torque over I0 times delta theta. The delta theta, this is going to be in radians, by the way, but we're going to move it over, and then you get omega naught squared times I naught divided by 2 tau f if you solve that equation there. Now, this is going to be in radians, so we got to convert it to number of revolutions. Number of revolutions is going to be the angular displacement divided by 2 pi radians. Why? Because every 2 pi radians is 1 revolution, right? So then this is going to be omega naught I naught over 4 pi tau f, like that. So that will be the number of revolutions there. Does this agree with our reasoning in part A? So what's going to happen is our reasoning of part A was that saying like, oh, when we add in a mass, we're going to increase the rotational inertia. So the I0 goes up. And if the I0 goes up and the N goes up, so we'll say yes. Yes. Increasing I0 will increase N, the number of revolutions. The number of revolutions. Okay? And that is how we handle problems like that.